Hi again. Now it's part 4 of the integral, and we're going to be taking a more interesting approach this time. We have two functions, and they intercept each other, and we're going to find the area in between them. So let's go ahead and take a look at the problem then. It is right here. We have the yellow curve, that is y equals 2 minus x squared, and then the purple one is y equals x squared minus 1. And as you can see, they intercept each other there and there. And our job is going to be to find the area that is all bound up right here. Now, we have talked earlier about how the integral can be interpreted as an area. And some of the problems have integrals where the area happens to be under the curve. And what it really is the integral down there was negative, but we can't have a negative area. But we'll be dealing with that shortly. So we see here that we have two curves, and from earlier, you remember that a second degree equation, when there's a negative in front of it, that it negative, the mnemonic was you frown because you're negative. So this yellow one has the frown, and this one, it's a positive 1 in this case in front of this curve right here. And because it's positive, it's happy and it smiles. So that was our mnemonic for remembering the second degree equations and how they look. And in our case, this shifts the curve up with 2. If we had a 3 there, the curve would go up over there. And then if we had a higher number, it would just keep going up that way. But it would still follow the same pattern. There we go, we erase that. Now the other one, the purple one, the number right there, the -1, that just shifts it down. If it was -10, it would just be further down the screen. Okay, we know that they're symmetric because it is a clean second degree equation, and the numbers in there only play the role of making it higher or lower, but the y-axis will still be a kind of mirror for both functions. And we're going to take advantage of that knowledge shortly. Okay, so now we know what we need to do, so let's get to work. We're looking for the area. Now you see that it's colored in green. We know something specific about these 2 points. And we know that because they intercept, that they have the same x value and the same y value. They're a point. They have those in common. And that is true for when they intercept and only when they intercept. So therefore, the two functions must be equal to each other there and only there at those 2 points. We're going to take advantage of that and set up a very simple little equation to solve. I'm not going to take too much time with it because at this point, that's last year's math, being able to solve those. So let's just see how it progresses and how it looks. And you simply just solve the equation. Put all the x's on one side, the numbers on the other, and you just go for it. And as you can see, I have put in this here. So the x is right there and right there. And then that gives us the point that we're looking for. Okay, so now we know what x needs to be in order for this to be true. Now we can take the next step. All right, let's do that then. We know that they're symmetrical, so we're going to take advantage of that and make our life just a little bit easier. You don't necessarily have to do it this way, but it is easier. If you just think that we're going to have our integration boundaries 0 and then over to the positive x over here, so in other words, from here over to this one here, okay, and then you multiply it by 2, since it's symmetrical, you're going to get the right area. When you multiply it by 2, it'll be the equivalent of filling in that other side. Like I said, you don't have to do it that way, but it is easier, and you'll see very shortly how much easier it is when you can have a 0 as one of your points. So symmetry is great to take advantage of when you can do it. And for those that are bored, you don't have to do it that way. You can do it the other way and test it, and see, you should get the same result. If you don't, you did something wrong. So let's look at that. All right, when we multiply it by 2, this is what happens. There we go. Now this 2 here is what I put right out in front, because see, we're integrating from there to there, from 0 to there, and that gives us half, so we multiply it by 2, and then we have the whole. So let's just take our next steps then. Let's see what we can do with this. All right. Now, here you can see that was the one function. Here's the other function. And some of you may be wondering, now how come we can do that? Well, if we look real quick, here was the one function, and it was, if we integrate, say, the whole side from there to there, we're going to get this. Okay, that's going to be the positive part. And then we had certain boundaries. We were going to cut it off about right there. But if we took it from the whole part that intercepted from the x-axis there, and then we cut it off there instead, we get something real nice and clean. But what does that mean? What does it really mean? See, this yellow one here, that would give us, if we use the particular points that we have, it would give us this much. A little hard to draw for me, sorry about that. And then we would have to get that much more for our particular numbers, the radical 3 divided by radical 2. Oh, and don't be bothered by having a square root on the bottom. It's going to eventually go away anyway. And for this, I just wanted to keep it clean. All right. Down here, if we look at the next function, that one, okay, down here, the actual value of the integral is negative, okay? And if we look at the purple part again, a little bit to the left, then we're going to have part of the purple bound here. This part of the purple one would be positive, just like this part of the purple, because it's whatever is bound by the x-axis and the function. So the two purple parts are positive, and then this part is negative. But what happens when you take a positive number, say up here, and take away a negative number? The equivalent of adding. So between the boundaries, from here to here, they take each other out in the proper way. So you have, in the one spot, you're going to have the yellow function that I had interacting with the purple function, and they exactly cancel each other out. And then when you get to this part here, where they start interacting the negative and the positive, you're going to be taking away a negative, which is adding a positive. So the area comes out to be the proper area. Sometimes you might have to be a little bit careful. Always keep in mind that the value of the integral can be positive, it can be negative, and the area is the interpretation of it. So if you end up with something negative, sometimes you need to do something to compensate for that and divide the integral up into little parts. We haven't done anything that complicated yet. So let's move on. I hope that makes sense so far. Let's just continue solving this. When you take the antiderivative, you get this amber colored stuff here, and then you're going to analyze it there and there. The zero is going to be nice and easy. We always like those. So let's take a look at it. Now it looks a little messy, but I'm going to go quickly, because if this part is difficult, then you just need to pause and review your early arithmetic, because this is straightforward now. This is last year's math or even earlier. So, but here at least I'll take one little comment, and you can see this is because of that zero there. If we didn't have the 0 point there, we would be having another big pile of numbers similar to that to take care of. So that's why, if you can get away with using a 0 and symmetry, do it. Okay, here's the next part. Now to help out with your basic arithmetic, I do it color-coded. So there's how this cleans up to the yellow. then the yellow cleans up to the purple, and then we get that, and lo and behold, we get the answer. And it's area units because nothing was specified. If it had been square centimeters, then we would have done that. All right, I hope that helps. We're going to be doing some more soon. We'll be coming up with part 5 and part 6, and doing some more complicated ones, and I think they're really fun, and they can make some pretty neat designs. All right, see you next time.